Yeah, thanks a lot. Indeed, I will also be talking about a very old subject, which is this particular model, the Ising model, lattice gas model, where you might ask also rightfully, what do you want to show us here? Okay, I want to give you a brief motivation in the next slide. This is actually all work done by a master student who finished his master thesis at the end of last year, Manuel. And we managed to turn this into two papers. So the first one is more concerned with the derivation of this functional that I'm going to talk about. And the second paper deals with an application which is born out by work I did in previous years with the Binder group and is concerned with the nucleation of droplets in finite systems. Okay, so the motivation is actually very simple. Isn't the Ising model actually the mother of all models in terms when you look at simple fluids and in particular on the liquid gas transition in such a fluid? I mean, it's so simple, you can't think of anything easier, I would say. And nevertheless, you get many characteristics of liquid gas transitions, in particular of criticality that have been used in the previous decades. The model is so simple that we have exact solutions, although only in 1D and 2D. We don't have full solutions for everything in 2D, say, only in 1D. Nevertheless, many precise methods in theory and simulations have been developed and tested on the model. And the question is, how do we fare with DFT in this context? Actually, it would be very desirable to add our beloved subject to these methods which have been tried and tested. But my experience was that actually the situation is not that good for the lattice gas / Ising model with DFT. So first, okay, to put the terminology right, so you all know the Ising model, it consists of upwards and downward spins. So there is a interaction usually favoring two neighboring spins in the same direction and disfavoring opposite spins. And you might put it also on a substrate, say an external potential, and then there is an interaction of the spin with this potential depending on the orientation of the spin. Okay, so the lattice gas actually is more a fluid model. So you have a lattice particle which is there, and if a lattice particle is there, you cannot put a second one there. So you have hard interactions, and there is next neighbor attraction by epsilon. And you could also put a substrate there, and there's interaction of the lattice particle, if it's there with the substrate, with an energy epsilon sub. And then if you try to match the partition functions of these models, then you find actually the energy scale or the interaction energy parameter of the Ising model is related to the lattice gas next neighbor interaction by this simple formula, and also the substrate interaction. So therefore, it depended on the taste of the researcher, whether he investigated or she investigated the Ising model or the lattice gas model. So these are really the same models. But again, for a fluid, from the fluid perspective, the lattice gas is more natural, I would say. There have been treatments, theory treatments out there, also in this notorious case of 3 dimensions. And especially I note here integral equation theories, which have come to very precise descriptions of especially the phase transition in the Ising model. I note here the so-called hierarchical reference theory. It's an integral equation approach which tries to incorporate the renormalization group in order to get critical properties right. Yeah? And SCOSA is I would say, competing scheme which does not impose any renormalization group ideas, but imposes a self-consistency of thermodynamics in the model, which also seems to be natural. And this then by itself generates also the correct or the more or less correct behavior. So both approaches are highly accurate. So this is just really amazing for the simple model. So here's an example. Okay, so this is the binodal for the lattice gas. So here's the density, which can vary between 0 and 1. So that would be 1, density 1 is each lattice side is occupied by a particle. This is the temperature on the y-scale scaled by the critical temperature. we see here the typical 3D critical behavior with this non-mean field exponents, and actually the HRT follows this curve rather correctly. And this is in comparison to an old Padé approximate result from the 60s. So SCOSA is there even better. I think also the critical parameter comes correctly within, I think, 0.1% or so. So one needs to be humbled by that. So this is a remarkable theoretical result, I would say. If you turn to the general inhomogeneous problem, so that is, we have an external field and we ask for the distribution and the free energy of our lattice gas particles, then the situation looks actually not that good. I mean, of course, we have density functional theory, but what I found in the literature are only RPA-like mean field functionals. So, and they have been mainly used as toy models to illustrate particular aspects of the theory and also for educating purposes, I would say. There is a very interesting method called the classical density matrix immunization group. So there the community is larger dealing with this in the quantum case, working out the Hubbard model, etc. But you can also formulate for the classical case, and you can generate close to exact results by that. It's a systematic procedure, and it is limited to simple geometries, flat walls, or a cubic box with an isotropic external potential on this box. So it's also certainly limited. So it does not include the wide scope of DFT. So we want to have a method which is actually very well applicable for all external potentials. So then we go to DFT. So that's actually we want to solve this problem by DFT. And here I give just the basic equations of DFT in terms of the grand potential functional, in terms of a particle density, which I call here rho C for rho colloid. So I see it as a colloidal model. And so one deals with a problem which has a repulsive and an attractive part in the potential, in the pair potential. And then you can split it in the usual way. The free energy functional split into the repulsive part, hardcore part, and this is exact. So this is the exact hardcore lattice free energy. It is local and actually very simple. And this is also contains the excess free energy of a 0D cavity given here in the grand canonical formulation. And Jim has shown to you also this form. And then the problem is, of course, the attractive part. And here, this RPA-like mean field approximation consists of this expression here. And so you have a sum over all lattice sites, and then for each lattice site, a sum over all nearest neighbors. And then you just multiply the densities at these two neighboring lattice sites, and you multiply with the attractive energy minus epsilon half. Okay, so this is I think one of the oldest functionals, and together it constitutes the mean field functional I want to compare with. Can one do better, actually? So the mean field functional is not very good, in particular for the Ising model, for the lattice gas. So if you look at the binodal, it ends up in the famous Bragg-Williams approximation, which has been designed also quite early in the history of statistical physics, and it is off by 70-something% in 2D. It's less in 3D, but it's not very good. An idea to incorporate the attractions is actually with a colloidal physics trick, and this is the Asakura-Osawa trick. So we generate the attraction between the lattice particles by depletion. And in order to do that, we add lattice polymers. And this is here an example in 2D. We add lattice polymers of size 2 for each Cartesian direction. And then actually the attraction between the colloidal particles here, the green particles, comes about. For each colloidal particle, there is an exclusion zone where the polymers can't be. So the blue PX polymer can't be here on that spot where the colloid is itself and on the leftmost spot. And the same applies to the PY polymer, so there's an exclusion zone for that. And if then exclusion zones for two colloids overlap, then you generate entropy for the polymers, and this translates into an effective attractive energy. And so the model is designed precisely like that. With these two types of polymer, you generate the Ising model, or the lattice gas. So, and then, well, you have to generate or to, come up with a functional for this colloid polymer system. And this is actually a very particular system. It's a non-additive hard system. There are no attractions anymore, but it's non-additive since the polymers don't interact with each other, but they interact hard with the colloids themselves. So in principle, you have shifted the complexity to this. There is a standard treatment for such AO models out. I would call this standard by now, and it's beautifully laid out in this review article by Joe, Bob, and Matthias in 2003. What you do actually, you take a multi-component hard body functional taken from fundamental measure theory. That's actually the best choice. And here in our case, you would have this formula formulated in colloid densities and polymer densities of different species. And then you linearize this functional into polymer densities, only the excess part. And by doing that, the polymer-polymer direct correlation function vanishes, and you end up with an ideal gas. And this is sort of what you want to do. The problem in the lattice gas is that this gives just the RPA mean field functional in all dimensions. So it generates also in one dimension, as well as in the higher dimensions, a model which has a phase transitions in all cases. And there is a reason to it, which shows up very severely in the lattice gas model. Actually, the polymer direct correlation function is not zero in the full model, but it has higher order terms in a virial expansion in the densities, and starting from a fourth order term, and especially for the lattice gas, these terms apparently are very important. So there's a second idea out in the literature how to treat lattice AO models, which had not been applied to the lattice gas before. And this has been formulated in a paper by Lafuente, Cuesta, and Matthias Schmidt in 2005. In fact, it was actually a comparison between the standard and the so-called Highlander treatment. And here, the idea is as follows. You make the polymers hard. So you introduce the size and polymer clusters. So you introduce new quasi-particles consisting of N polymers of one species. And if you have another M polymers, then this is a different species. So these two species cannot coexist on the same lattice point, because then it would be a polymer cluster of N plus M particles, which would be a third species. So you blow up the species space, but the advantage is now all species interact as a hardcore lattice gas. And then you try to construct the excess free energy through methods of this lattice fundamental measure theory. And Lafuente and Cuesta could show that in one dimension, the colloid polymer cluster system is actually minimally non-additive. So it's actually, there's a non-additivity only of one lattice side. And in that case, lattice fundamental measure theory is exact. And the proof is, as I understand it, actually very similar to what Jim has sketched in the hard rod case. It's just here the colloid case. You construct the explicit mapping between external potential and density, you invert it, and you find the functional. In higher dimensions, the whole thing needs approximations. The polymer clusters are of different species now. They are still ideal with respect to each other. This is our approach. And lattice FMT is not exact even for these minimally non-additive models. Okay, and then we construct this functional as follows. So we have this AO model in the standard formulation. Then you map it to this polymer cluster model, where the polymer clusters become hard. And then we construct the excess free energy with this dimensional crossover. And here's an example how this result in 3 dimension actually looks like. So this is here, phi is the usual free energy density for the excess part of the free energy. And we have here 10 weighted density in the 3-dimensional case. And the weighted densities are either local densities in terms of colloids and polymer clusters, or some non-local densities for a combination of colloid and polymer cluster densities. So the advantage of this Highlander treatment is that in the end, we have only one polymer cluster density for each polymer species, which is actually a sum of all cluster densities of different particle number in the cluster. So actually, this blow up is actually reduced again back to the original number of polymer species which you have in the model. Okay. So a very nice outcome is, which had already been shown in 2005, that in one dimension, you get the exact functional. Yeah, so you get the exact density functional also for the Ising model in one dimension in this, with this procedure. And in 2 and 3 dimensions, not exact. So here are some results on the phase diagram. Okay, so the left plot is 2 dimensions, the right plot is 3 dimensions. And here's one example. 2 dimension is notoriously difficult. I mean, the critical point here in this beta epsilon units is 1.76. And this Bragg-Williams approximation puts the critical point at 1, very far away. And here we are at 1.4 something, which is closer, but not very close. And this looks better in 3 dimensions, where the distance has been reduced considerably to the exact result or quasi-exact result by simulations. It is interesting to note that the Highlander binodal is actually the Bethe-Pyles approximation, one of these very famous other approximations in the Ising model. And apart from mathematics, we have no real idea why this is the case. And here is a result on the surface tension of the gas-liquid interface. And actually, we see here the nice result that in 3 dimensions, we're coming very close to the actual simulation results. It's not the case in 2D. There are exact results available through Onsager's method in solving this. We notice a very funny phenomenon about the liquid-gas interface in a lattice model. Okay, let's start first. I mean, the lattice, the density profile for liquid-gas interface is defined discretely. So you have lattice positions here, and then you have a density describing transition from liquid to vapor. And there is a discrete translation symmetry. You translate the whole density profile by one lattice unit, and everything is conserved. And for this free interface, we know the standard properties, the chemical potentials at the coexistence value between these 2 phases. The equimolar position is actually in the middle between these 2 lattice sides. Equimolar position is defined, you have no net absorption at the interface. So actually, the amount with which you go down with density from the liquid is the same amount of particle numbers density with which you go up when coming from the gas side. So this is the meaning of the equimolar position. And we have this noted invariance. But now what you can do is you can design a finite box. You can make it very large, but nevertheless finite. And you can fix or constrain the equimolar position of the interface at an arbitrary real position. Now, this is just a constraint that you put in with a Lagrange multiplier in minimization, in the minimization procedure. And then we find something very peculiar. Indeed, we are able to shift the whole density profile continuously through 2 lattice sides, between the space between 2 lattice sides. And we generate also quite different density profiles there. And these are solutions which are not at the coexistence chemical potential. So these are, so here is the offset of the chemical potential for these planar interface solutions. There's planar, there's a planar symmetry. But we have a variation of positive values from the coexistence chemical potential to negative values, and then return within one lattice unit here. And also the surface tension becomes now kind of dependent on the definition of the equimolar position or the position. And the surface tension has this particular loop here. The minimal surface tension has been reached for the free interface, as is expected. The free interface belongs to these two density profiles here, which are related by just a shift of one lattice side. And then we have a number of other profiles, and there's also a maximum interface tension belonging to this profile where the equimolar position is just on the lattice side. So this is a very funny finding. It has actually not really been noted before. It has been noted in some zero temperature considerations on the statistics of the Ising model. But it's actually quite natural that for discrete models, you can put interfaces under stress. And I think one can also generalize it to interfaces between solid phases. Okay, this intermediate summary is that, okay, we have improved a lot, I would say, RPA like mean field DFT, but we're still some distance away from a quasi-exact functional. But the AU route would actually require more work on hard lattice models for further improvement. Now there comes the second motivation. We applied this to droplet nucleation, and this is a basic process for transforming a gas to a liquid. And the formation free energy of critical droplets is actually the thing one is usually after. Now, critical droplets in a supersaturated vapor are actually metastable in standard density function theory. So you can stabilize them in simulation and in theory using finite systems, actually, finite boxes. Up to now, actually, a direct comparison between simulation and theory was difficult because the use of different boxes and also simulation has a residual translation entropy of the droplets, which is a bit hard to get or to subtract from the results. And actually, simple lattice models seem to be a rather good testing ground for advancing this comparison, I would say. So first, standard van der Waals picture of thermodynamics in the coexistence regions like that. Okay, you have here the free energy density, you have a common tangent, you have a vapor liquid density, you have metastable states up to the spinodal points, and in this region of metastable states, you have nucleation. So this is also the realm where you can generate stable droplets in finite systems. And then between spinodal points, you have unstable states. If this translates to the chemical potential in the following manner. So there is the coexistence chemical potential here, and there is the standard van der Waals loop of the chemical potential. Now, if you put the system into walls, so you have a finite system, then actually the shape of this new equation of state, as I would call it, is quite different from the van der Waals loop. And this is due to these appearing stable droplet states. You have a sequence of a supersaturated vapor to a droplet, to a cylinder state, to a slab state, and then in inverse droplets, so a gas bubble, gas cylinder, gas bubble to the homogeneous liquid again. Yeah. And then if you make the system actually bigger and bigger, then this van der Waals-like portion vanishes, and you end up actually with a flat chemical potential across the whole coexistence region. But you can actually exploit this stability of these droplet-like states in order to get the properties of the droplet. But actually, just to show you, this is indeed what we find when we minimize our model in these finite systems. Okay, caveat noticed here. I mean, we don't use a finite n density functional, but we use the grand canonical functional with just a Lagrange multiplier on the number of particles. But we expect actually for the number of particles that we have here, there's not a big difference. And here you see this new equation of state. So this is the van der Waals loop from the homogeneous free energy. And this is the chemical potential in the finite boxes. And we see the sequence of droplet, cylinder, and slab. And this is still fairly close to the critical point with the Highlander functional. We find also lattice peculiarities. That is actually the chemical potential begins to oscillate in the slab portion, has undulations in the cylinder, and also slight irregularities in the droplet portion. And this is actually well, the oscillations in the slab part are actually the oscillation for constrained planar interfaces that I've talked before earlier. And then the undulations in the cylinder droplet part are sort of leftovers from droplet layering transitions. And if I have time, I would say a final word in the end. This all occurs at lower temperatures, higher interaction energies. If you want to extract thermodynamics of droplets, you define usually two radii of droplets. Actually, the position of the interface is quite arbitrary if you have a continuous density profile. So the usual two choices are the equimolar radius and the radius of the surface of tension. At the surface of tension, the usual Laplace equation holds, and you assume a spherical droplet. And this all implies that the surface tension is radius dependent, and one has to keep this in mind. Old work from the 1950s imposes a consistent relation between the surface tension, the radius dependent surface tension, and the radius dependent difference between the equimolar and the surface tension radius. And this difference is usually called Thorman length, and it's quite an interesting quantity. So what you have to do is actually, you have to sort of come up with a useful expansion or functional form for, say, the surface tension or the Thorman length in terms of the radius of the surface of tension. And then this Gibbs-Thorman König-Buff equation can be used to get the other quantity out of the first quantity. Okay, and here's, I would say, here's the expansion that we used in our studies, and the expansion is motivated by different facts. You would naturally assume that there's a 1 over r expansion. 1 over r is the radius of the droplet, but there are also logarithmic terms, and the logarithmic terms are actually suggested by renormalization group studies. Yeah, and the 1 over r expansions are also naturally occurring in DFT-like models, as had been shown in older studies on the Lennard-Jones system here before. So renormalization group actually finds a fixed coefficient for this leading logarithmic term, and I will come to that also in a second. And then actually, if you do this all for the Ising model lattice gas, then you find this Thorman length in the limit of infinite radius is actually 0 due to gas-liquid symmetry. So actually we expect an expansion of the surface tension. There's a constant term related to the planar surface tension, and there's a log r divided by r squared and a 1 over r squared term as leading corrections. So these are typical results here, numerical results. These are the symbols for the surface tension as a function of this inverse radius. This is still close to the critical point. And we tried to fit these results actually with 3 fits. One is imposing the renormalization group result for the logarithmic term. And we fit the 1 over r squared term and this planar surface tension. We fit all 3 coefficients, and the fit 3 is actually we put the log coefficient to 0. So the surprise was here, fit 3 was actually the best fit. Sorry, fit 2 was the best fit, which described all the results. Naturally, I would have expected fit 3 is the one, because I would assume there is a 1 over r analytic expansion, and there's no log term in the DFT model. But it turns out that actually the consistency of the gamma expansion and the delta expansion with the GT-KB equation requires a small log term. But the DFT, we do not find the renormalization group result, and I think this is to be expected. Okay, so this is also summarized here. So the DFT results are actually not compatible with the logarithmic contribution. But the advantage of DFT is very often that you get very good free energies, in our case, the surface tension, and you try to get these, or these very good results are generated by a different analytic form. So the reason is most probably the failure of the functional in the critical region, and one would need more additional work to get this more right. And this small logarithmic contribution is needed to maintain this consistency. The size dependence of the surface tension in the Ising model comes mainly through this 1 over r squared term with this B coefficient. And here's actually a comparison between the mean field result and the Highlander result. And we see actually the correction from mean field to Highlander is substantial. So we have more than 100% shift in the reduction of the surface tension of the droplet. So this also says that one should put work into the form of density functionals for attractive systems in order to get this size-dependent surface tension. Here's this amusing side finding, which is related to these undulations in the chemical potential equation of state here. If we look at the problem in 2 dimensions in mean field, then we find a very peculiar transition, and we call this the droplet layering transition. So look at the mu equation of state here. So again, this is the sequence of a drop in 2 dimensions going over to a planar interface. So there's no cylinder here. These are the undulations, the oscillations due to the constrained planar interface. But if you look at the portion of the chemical potential in the droplet section, you find sharp jumps in the chemical potential. If you have sharp jumps in the chemical potential, this is a phase transition. And we can analyze this by looking at the density profiles. And so here, this is the parameter we vary in the finite box, namely the mean density. This is actually the behavior of the radius of the surface in tension and then the equimolar radius. The equimolar radius is a continuous function and the surface of tension jumps. And these are the associated density profiles. And now we look, for instance, at a density profile at this section, quite close to the jump, and here on the other side of the jump. And here we see that it's really just one layer of lattice gas particles is added on top of the surface. And the same thing happens here at the second jump from these diamonds to the red triangles. It's really adding one discrete lattice layer to the droplet.
Martin, it's 5 minutes, including the discussion.
Right, and I'm already at the end. Excellent. So what I've shown is actually the critical droplets are well describable in DFT. And it was worth, I think, to work on this better functional because the size-dependent surface tension strongly differs. And we have more hope that these results are better now. But I want to repeat, looking at the bulk results that we had, we are still some distance away from a quasi-exact functional seen in comparison to, say, randomization group studies. And it would be still a challenge how to incorporate this into DFT. And with that, I thank you, and I'm happy to get questions.
Oh, we thank you for your talk on behalf of everybody.